Welcome to this lecture on pole placement through state space techniques. We will introduce the state space techniques, we will present the state feedback control problem, we will conclude this lecture with problem formulation. Let us start with our standard state space model. Recall that we introduced this delta. X is a state, U is a control effort, and in this particular case we take U to be a scalar, that is only one control effort. We also assume that all states are measured. Later on in this week we will relax this assumption. The question is, can we use a state feedback controller to get a desired closed loop characteristic polynomial? So let us take Z transform. So because you have x of k plus 1, by the shifting theorem you get Z here, Z into x of Z, then you have AXZ, BUZ. Similarly for this x naught into Z, because of this k plus 1 you have a Z, and of course Z transform of delta is 1. Let us bring this to the left hand side and write down the other terms. Let us take this to the right hand side. So x of Z is Z minus A inverse into BU of Z plus dot dot dot, and now let us take the inverse of this. It is adjugate of Zi minus A divided by determinant of Zi minus A times BUZ. This is the standard formula for calculating Zi minus A inverse. Now I have a question. We have a transfer function here and hence there are poles. Is there any relationship between the eigenvalues and the poles? In this slide we will show that the poles of a transfer function are the same as the eigenvalues of the underlying matrix A. So let lambda denote eigenvalues and V the corresponding eigenvectors. So we have the standard relationship. Roots of Zi minus A or lambda I minus A equals 0 give eigenvalues of A matrix. Let us take this example. A is this 2 by 2 matrix. Let us calculate Zi minus A. We get this matrix. Let us find the inverse. So we have the determinant of this matrix here. Because it's upper triangular, you can calculate it directly. And then here is the matrix that you get by exchanging the diagonal entries and changing the signs of the off diagonal entries for a 2 by 2 matrix. So you can see that it has two poles 1 and 3 from the denominator here. These are also eigenvalues of A, as you can see from this upper triangular matrix. Now let us recall our requirement and state space model. Here is our state space equation, and we would like to use state feedback control law. So the control law is of the form uk equals minus kxk plus vk. So this x is the state, it is a vector, it could have n components. So I write it like this: x is x1 through xn. So k also has to be the transpose of a vector which also has n components, plus v. What is v? V can be thought of as the offset. Now substituting this expression into the state space equation, we get the following. where we have substituted for u from here. And remember, in this expression for u we substituted and we got this equation. All other terms are same as before. By grouping terms, we get a minus bk into x of k from here, and then bvk plus this offset term. The question is there a k that will make the system behave better? What do I mean by that? The original system is given here, and the dynamics of this are decided by the eigenvalues of A. Now, with a suitable choice of u, we obtained this expression. Now we no longer have A, but we have A minus bk. Can we choose k so that A minus bk behaves better? That is a question we ask. So let us consider an example. Here is the A matrix 2 by 2 example, and we have arbitrarily chosen this example. The eigenvalues are 1 and 3 and hence unstable. That means A is not well behaved. What about A minus bk? So let us substitute for A and B here, and k is yet to be decided, so we write it as k1 k2. When I simplify it, that is multiply this out, I get this second matrix, and let us subtract, so I get this. Suppose I arbitrarily choose k1 to be 0.5, k2 to be 3.5, then we can get A minus bk to be minus 0.5 here and minus 0.5 here also. You can verify that the eigenvalues of this matrix are given by this expression, the magnitude of which is 0.7071, which is less than 1, and hence this system is stable. A minus bk has eigenvalues inside the unit circle, and hence this is stable, whereas the original A matrix is unstable. Now let us close the loop. Here is our state space equation, here is the feedback control law. What is meant by closing the loop? I substitute for u in terms of this expression into the first equation. That is what is meant by closing the loop. So let us go and do that. In the place of uk, I have substituted this and grouped the x terms. I have got this as we saw in the previous slide. By the way, in the rest of the lectures to be covered in this week, we will keep recalling this closed loop expression. So it is an important expression. Let us take Z transform of this equation. So because I have k plus 1, I get Z here, Z into I. Then I bring this term on the left hand side, I get A minus bk. Then I have x of Z equals bvz plus x naught into Z, which is the Z transform of delta of k plus 1. Now let me take this matrix to the right hand side and expand this in terms of adjuvant and the determinant, and the denominator is the closed loop characteristic polynomial. So let me start with that expression Zi minus A minus bk. We want this to be equal to some arbitrary polynomial, nth degree polynomial. The coefficients alpha 1, alpha 2 and so on up to alpha n decide this polynomial. You can also factor this through these n factors, we could possibly arrive at this polynomial through the desired region analysis that we discussed in the first part of this course. Question: how does one find k to satisfy this requirement? Notice that I have nth degree polynomial here. Remember that A is an n by n matrix, k also has n components, k1 through kn, and here we have another polynomial that is of degree n, it has n coefficients. What are the unknowns? B is the unknown. What are the unknowns? K is the unknown, k1, k2 all the way up to kn, A and B are given. So the question is, how does one find k to satisfy this, and can one always find such a k? As I mentioned earlier, one can equate the coefficients of this polynomial with those of this requirement, but this is not an easy problem to solve, because when we equate the coefficients we will get n equations. They will be nonlinear, they may not be well behaved, it may be difficult to find initial guess, and so on and so forth. So it is not an easy problem to solve. We will show in this week that if A and B are in controller canonical form, what is it? It will be explained in a subsequent video. Then k can be easily determined. That is, in general it is a difficult problem, but suppose A and B happen to be in a specific form, then it is easy to determine the unknowns k. To conclude this lecture, the eigenvalues of a system matrix are nothing but the poles of a transfer function, and pole placement problem becomes solving a polynomial equation, which is a difficult problem. A simpler approach will be explored in subsequent videos. This brings us to the end of this lecture. Thanks for joining. Goodbye.